ass up like I should. Drop it like gravity. Ass is up, ass is up, ass is up. Then drop it like gravity. Ass is up, ass is up, ass is up. Then drop it like gravity.
So we're trying to understand more about gravity, for example. Why is gravity so much weaker than all the other elementary forces we know about? That is to say, the three other elementary forces we know about, electromagnetism,
Right.
and weak and strong nuclear forces. Gravity is far weaker. I mean, if you think about it, you can pick up a paperclip with a tiny magnet competing against the entire Earth. And the fact that you can jump up and down, I mean, gravity is not a strong force.
And when things fall, they break because gravity is strong. The fact of the matter is that it's not strong. It's really a very weak force.
Gravity pulls us down to the Earth and keeps our Earth in orbit around the sun. But in fact, we overcome the force of gravity all the time. It's not that hard. Even with the gravity of the entire Earth pulling this apple downward, the muscles in my arm can easily overcome it. And it's not just our muscles that put gravity to shame. Magnets can do it too, no sweat. Magnets carry a different force, the electromagnetic force. That's the same force behind light and electricity.
It turns out that electromagnetism is much, much stronger than gravity. Gravity, in comparison, is amazingly weak. How weak?
The electromagnetic force is some 1,000 billion billion times stronger. That's a 1 with 39 zeros following it.
The weakness of gravity has confounded scientists for decades.
Did it work? Anyone? Anyone know the effects? It did not work. Today, we have a similar debate over this. Anyone know what this is, class? Anyone? Anyone? Anyone seen this before? Anyone know what this says?
People are wrong on so many levels. I'm referring you to the actual source materials, Albert Einstein and his special and general theory of relativity. It's very short. I think it's only about 80 pages long. Very simple to understand. But I'm going to refer you now to section 18. This is the section that deals with all things being equal. In other words, if we're all in the same gravitational field, such as the Earth's gravitational field, all objects, forces, physical principles within that same gravitational field of the Earth act as though they are relative to each other. Therefore, because the great G, the gravitational mass, is on one side of the equation, and the gravitational mass is on the other side of the equation, then you've got your force equations, such as electromagnetic forces between two objects, or Maxwell's equations, or whatever. The fact is that GM and GM are equal on both sides of the equation. So like simple algebra, you just cross through the gravitational mass because they're equal, and you do the equation as if you're only working with those individual forces that are acting relative within the same gravitational field that's equal on both sides. That's the general principle. All objects within the same gravitational force act relative to each other. Next, I'm going to refer you to section 19 of General Theory of Relativity. And I believe these might be the only equations. Well, they're not the only equations, but they're the significant equations. So what he uses, according to Newton, force equals inertial mass times acceleration, or you can say speed, speed of light, inertial mass, and he defines what inertial mass is. Inertial mass is interchangeable with gravitational mass, gravitational fields, and weight. They're all interchangeable terms. And what is this calculated in? They're all calculated in kilograms. So you're going to have this acceleration, or his force gravitational equation. He says force equals gravitational mass times the intensity of the gravitational field. And what is the intensity of the gravitational field? Well, over on the next page, he tells you, you times the gravitational mass, or its weight, by its gravitational field, and or the speed. And that's weighted in kilograms, and the speed of light. So all things being equal, gravity made up of c squared atoms has much more gravitational force than any object within it, such as, think of the elephant. It's how much does the elephant weigh? Well, the gravity weighs how much more than that? It's the mass of the earth. That is the force of the earth, okay? I'll try and make it a little bit more simple by breaking down these equations. So here's the Wikipedia page on the mass of the Earth. And as you can see, the mass is 5.9722 plus times 10 to the 24th kilogram. In the US, that means approximately 1.3166 times 10 to the 25th pounds. Okay, this is the energy, or the mass, or the inertial mass, or the weight, as Einstein defines in his section 19 of his general relativity theory. This is the force of the Earth. So the force of the Earth is its gravitational field. So anything acting within it, such as the electromagnetic force, such as let's see, this frequency of sound. All of it is added to this equation. So you're going to have the electromagnetic force, such as Brian Greene said, which is a billion times stronger than the Earth's mass. Okay, you're going to have that figure, plus then you're going to add the weight of the Earth. So what's going to be stronger? It's going to be the electromagnetic force with all those zeros behind it, plus you're going to have to add in this to get the total of the equation. So I'm going to break it down even further. So I pulled out some of Einstein's definitions. Einstein's General Relativity, section 19, Einstein defines gravitational mass equal to its inertial mass equal to its weight in kilograms. So for every particle composing the Earth, you're going to weigh it in kilograms. All three terms are used interchangeably, and they mean the same thing. Now, inertial mass means gravitational mass, means weight in kilograms, means gravitational field, because that's the force that's exerted outward by the mass of the Earth. So what has the stronger force based on its inertial mass defined by Einstein's? Let's take the bar magnet example used by both Brian Greene and the female physicist. Let's do the math. Okay, we've got Earth's inertial mass at 5.97222 times minus 26 times gravitational constant. Then you have the bar magnet. Now look at the bar magnets. It's only 1.36 grams times the Earth's gravitational field. What's that going to be? Let's just times it by g. Well, it's going to be less than the inertial mass of g times g. It's only going to be 1.3 g's times gm. See that? So the bar magnet only pulls up the little paper clip. Let's see, this is inertial mass of a wire. This is the paper clip. The only reason why the bar magnet pulls up the paper clip is because you have to add gravity to both sides of the equation. So here we've got GM. So you're going to have 1.36 grams, which is the bar magnet's electromagnetic force or field, time equal or greater than, well, of course, this is 0.40 grams. So 1.36 grams times the gravitational mass of the Earth is going to be greater than 0.402 grams times the gravitational mass of the Earth. But of course, in physics, what you do is you just get rid of these because they're equals on both sides of the equation. That doesn't mean it doesn't exist. It just means, as section 18 of Einstein's theory, it states, when you have a bar magnet and a paper clip within the same gravitational field of the Earth, they act relative to each other as if the Earth's mass didn't exist, because the Earth's mass is equal on both sides. So you just, like in simple algebra, cross it out. That doesn't mean it disappears because you've crossed it out on your paper or in your math equation. It's still there, and to have the full equation, you have to add it back in. Okay, so let's work again on what is a force? Force equals mass times velocity or speed. He says acceleration, but you can say the speed of light. Force equals the gravitational mass divided by the inertial mass times its gravitational field. So it's gm times g. It's g times g. The full on the same side, you're going to have them equal. And then here, we're going to get into just how we can escape the Earth's gravitational field. Well, let's do the electromagnetic force. Which has the greater inertial mass force, the Earth or the electromagnetic force? I'm going to let you do the math and look it up because that's good for you. But the short answer is the reason why electricity and magnetic field lines bend in the Earth's gravitational field is because the Earth, a greater mass, a greater force, is acting upon the electrical and magnetic field lines and bending them. Otherwise, electricity would just go straight up and never come back, and the magnetic field lines wouldn't bend, and they wouldn't be perpendicular to each other because they're both trying to escape, but they can't. They have to bend around and take right angles, just like short-sided metric says. Electric goes one way, magnetic goes at a perpendicular, and they hit each other, and they've got to spread out again and hit each other because they're hitting a wall of the gravitational outside field of the Earth, which you can't escape from, and that brings us down to what is escape velocity. Okay, I'm going to put on a short video, and you need to watch it so you can understand.
Okay, I want to tell you about escape velocity. Escape velocity, let's define it as it's the minimum launching velocity required for an object to never return once it's launched. So you're going to shoot something off of the Earth or any other planet, and it's going to take off, and it won't ever come back. It won't turn around and come back to the Earth. But a couple key things. It's the minimum speed for this to occur. So you can go faster than the escape velocity, and it for sure won't come back. But what is that minimum speed that's necessary for it to never come back? Okay, so how do you figure out escape velocity? Well, the bottom line is if you don't want to be bound to the Earth, you have to have a total energy of 0. So that's how you figure out escape velocity. So like if here's your planet, and you're gonna take off and never come back, then what you would like to do, we're going to do an E equals E prime. So E equals E prime. So the E, when you take off, you have you're going to have kinetic energy, 1/2 mv squared of the rocket. So I'm going to say, let's call it the rocket m sub r, Vr squared, plus negative g times the mass of the rocket times the mass of the Earth all over the radius of the Earth, not squared. This is the potential energy of the rocket Earth system. So right there, that's how much potential energy it has right there. And this is how much kinetic energy it's going to have right there. Now, when it gets really far away, we would like it to have, if it's the minimum speed it can have and still never return, then we'd like it to get to infinity and have no energy. So at infinity, we would like the velocity to equal 0. We don't. If it gets there, if it gets to infinity with more than 0 velocity, then we could have sent it slower. Okay, so that's going to equal, a lot of space there. Then the E prime is at infinity. So this is at the surface. I'll call it E at the R of the surface. And then this is at infinity. Now the energy at infinity is kinetic energy. That's a prime for later on. Plus G, mass of the rocket, mass of, say, the Earth. And then this is at infinity. So RE, how far away is the rocket from the Earth? It's an infinite distance. Oh, and by the way, we'd like this to be 0 too. If that's 0, then this whole thing is 0. And if we divide a number by infinity, you might guess when you divide any number, finite number by infinity, it goes to 0.
Did it work? Anyone? Anyone know the effects? It did not work. Today, we have a similar debate over this. Anyone know what this is, class? Anyone? Anyone? Anyone seen this before? Anyone know what this says?
I only gave him a buzzard because while the equations he does are accurate, he tries to explain at the beginning of his video why NASA can shoot a rocket into space. And I suppose he's trying to state that their little rocket fuel, solid rocket boosters somehow are able to absorb the entire mass of the Earth plus some and reach into orbit. Total nonsense. The math doesn't support that kind of thinking. And I think who knows why he said something. They've known this forever, that you can't escape the gravitational field of the Earth, because to do so, you would need the entire mass of the universe, and that's what the escape velocity equations state. Escape velocity is E1. E prime defined as infinite energy. What is infinite energy? Infinite energy is the only thing we can imagine now is 0 point energy, or the entire energy of the universe is needed to escape the Earth's gravitational field. And not even a photon, the photon cannot escape it, because while the photon at its resting state is considered massless or near 0 point, at its quantum state, or at its highest velocity state, at its highest speed or energy absorption, a photon has inertial mass equal to 4/3 of c squared, or that's going to be c plus 1. That's going to be c squared. 4/3, well, that's going to be c squared. Photon is considered massless. Let's just look at the electron. The electron, it has mass, and it's going to be, its inertial mass is c squared times 1/4 c, but the photon, which is considered near 0 point, has inertial mass, and its inertial mass, I think it's been determined to be 1/3 of c. So it can distort itself by c times 1/3 c, I believe is the equation, but I'm going to have to look that up. But the concept is that the quantum level is its velocity level. Light, as it travels, distorts and has inertial mass. it can't even penetrate the 0-point energy produced by the Earth's gravitational field. In order to escape Earth's gravitational field, the equation requires infinite energy, which is the entire energy, not of the Earth, but of the entire universe. So says the math.
Look at the forces. Notice the common term gm over r squared. We are going to call this the gravitational field strength, denoted by small g. Now we can replace all the gmm over r squared with mg. Basically, we imagine that the Earth produces a gravitational field around it, and it's the field that exerts gravitational forces on all the masses sitting in it, causing them to undergo gravitational acceleration. Restricted to a localized region, such as the surface of the Earth's gravitational field seems uniform, always downward, and the field strength is constant in magnitude. On an astronomical scale, the Earth's gravitational field is clearly non-uniform. It's directed radially inward, and the field strength weakens away from the Earth, according to the inverse square law.
So how do so many experts get it so wrong? Well, as Upton Sinclair once said, it is difficult to get a man to understand something when his salary depends on his not understanding.
Ass up like I should. Drop it like gravity. Ass is up.